One of the solutions is to design memory constraint algorithm. What is that? So such algorithm use less memory space, and it is known that there is trade-off between size of space and learning time. The motivation of my research is as following. So recently, CPU is faster and memory is cheaper than before. So we can handle problems of larger sizes, which leads to new direction of computation such as data streaming, massive parallel computing, and so on. So we need space-efficient algorithms with less memory space. So our primary objective is to obtain some space-efficient algorithm for fundamental problems and to establish good space-time trade-offs. So to design memory constraint algorithm, we have to define our computational model. So we assume that the input data is stored in a read-only space and output data is stored in write-only space, which means no reordering elements in them is possible. That is, we cannot handle as workspace in algorithm learning. But we can use a classical random access machine, so we can random access to our elements in a read-only space. The workspace we are using for an algorithm is additional memory space, which allows to read rewrite elements, also deleting and so on. It's as usual workspace. So we provide two types of memory constraint algorithm. So first is it's called adjustable workspace algorithm. This other is a small workspace algorithm. Let's say non-adjustable workspace algorithm. So first one is such algorithm performing on arbitrary size workspace. The second is algorithm using less workspace rather than input size. Let's say n. So for example, using on workspace using only log n bit or n log n bit or just only n bit. So in this talk, I'd like to talk about one small workspace algorithm, the problem of the tips for search. Okay, let me explain specifically about small workspace algorithm. Such algorithm allows to use limited size workspace. The size is decreased as much as possible. For example, log space computation is known as a small workspace algorithm in computational complexity theory. So that workspace is can be used only constant number of variables. The given input data of size n, so each variable has equal log n bits, which is enough to store a pointer and for a number. So this is the result of log space computation provided by Lion Gold in 2008. So she showed that SD connectivity for undirected graph can be solved in using only log n bits. Okay, next, so I'd like to explain about this first search using only big O of n bits. So first, this first search is for given graph G and with limited space, and the number of bytes is n and the number of edges is m. So this first search is a fundamental algorithm for searching on a graph. It's expressed as much as possible along each branch before backtracking. So a simple implementation using n of n bits. So our QRC question is, can we make DFS algorithm in small o n of n bits? So then our answer is yes. We can using only before and bits. So what is this first search problem? So input is a directed for undirected block with n buses and n edges. Then output is a DFS tree. That means if we given in the block, then this first search is returned to the order. Searching order, it means A, B, F, G, C, D, E, B. We usually use analog and bits to construct the first search. So because it's easy to backtracking. The vertex located in the top of the stack is always the next vertex to be listed. This figure shows this state. We are now vertex E. Then we have to find the next unvisited vertex. It's C. Then look at the stack, top of the stack. So it's C. So we back to the branch of C and we find the next unvisited vertex. So, but we have to use only BICON and BIS to construct DFS search. So what is difficulty is we can hold buses to be listed next. So its solution is to find such buses by tracing graph in many times. So we provide a 4-color DFS. We use only in DFS, we use only BICON and BIS, and we maintain buses with 4 colors: white, gray, blue, and black. Okay, let's talk about the algorithm. So let S be a search starting vertex. Then its algorithm consists of 4 stages. Initially, all buses are colored white. Then all colors change to black. Then the DFS is greenish. Initially, so we color S to gray and set U to S. And in stage 1, we find first unvisited vertex again and again. So first we are now A, and next destroy 5 vertices B, and F, H, I, and C. So look at C. It doesn't have next white neighbor vertex, so it's the vertex N. Then move to stage 2, and we find black vertex, backtrack vertex, which means that we back to starting point, then we tracing gray vertex. It means in this figure A and B and F and so on until arriving to C. So, and we find vertex W just before V. So, and stage 3 corrects V to black because the vertex doesn't reach anymore. And again, we back to a starting point, tracing a blue vertex until V. Then we start again stage 1. I mean, searching the next white vertex again and again. So it proceeds to DFS algorithm. So the running time algorithm is equal of nm time, because for each iteration, at least one vertex is colored black during tracing. And space is 2n plus big O of n bits. So each vertex needs 2 bits for maintaining 4 colors. So let me conclude my talk. We provide a simple, non-adjustable workspace algorithm for search. We also designed adjustable workspace algorithm for fundamental geometric problems. So, for example, finding shortcut